Okay, imagine this. You're running a high-speed CNC mill, parts are stacked, the cycle time is just dialed in,
Right. Everything's running smoothly.
and then the whole thing just hiccups. That smooth, precise dance of the automatic tool changer, the ATC, it turns into this sudden, awful metallic clunk.
Oh, that's a bad sound.
It's stuck. Your machine isn't cutting chips anymore. It's just this expensive monument to frustration.
And that sound is the sound of money just evaporating.
Yeah.
I mean, a jammed ATC is one of the quickest ways to zero out your entire daily throughput.
The pressure is on.
It's immediate and it's intense. But the good news is that these critical failures, they're almost always predictable.
And that predictability is exactly what we're here to conquer. Our deep dive today is, well, it's custom tailored for you, the operator or maintenance tech who's under pressure.
Yeah.
Who needs that specialized knowledge to diagnose, to safely fix, and most importantly, prevent these ATC meltdowns without having to wait hours for a service call.
Exactly. We've sort of distilled the core knowledge from experts in the field of machining centers. And what we see, I mean, across virtually every type of machine, is that ATC issues are concentrated in 3 zones.
Okay.
You've got pure mechanical wear, you have unreliable pneumatics, or you have confused electronics, basically the sensor system.
So before we even think about grabbing a wrench, what's the immediate triage?
Yeah.
That error code flashes. What 3 checks have to happen right away?
Triage is simple, and it's fast. First, physically inspect the arm and the magazine. Is there, obvious chip buildup or physical damage?
Just use your eye.
Use your eyes. Second, look at your machine's air gauge. Is the pressure holding steady? Is it high enough? And third, pull up the machine diagnostic screen and look at the sensor feedback. Don't assume anything. Verify all 3 immediately.
And the preventative baseline, the thing that stops this from happening in the first place.
Regular cleaning and lubrication. I mean, downtime is measured in thousands of dollars. A daily wipe down is measured in minutes. It's the cheapest insurance policy you can buy, period.
Okay, let's start by recognizing the enemy. If you're not sure what kind of failure you have, you'll just waste time chasing ghosts.
Exactly.
The sources break this down into 4. Let's call them 4 distinct buckets of failure based on the immediate symptom.
And you can think of these symptoms as flags. They're telling you exactly which system is accuracy, mechanics, or electronics is actually compromised.
Let's start with bucket 1, the missed handoff. This is an accuracy problem.
Right. So the arm completes its swing, but the tool is misaligned, often by just a hair ½ millimeter, maybe 1 millimeter.
That's right.
It looks correct, but it fails that final check. It's subtle, but it's deadly for production.
So how does the machine tell you it's a failure of precision and not, a hard crash?
The immediate sign is that the drawbar will attempt to clamp, but it cannot securely grab the pull stud on the tool holder.
So it can't get a grip.
Can't get a grip. The control system immediately throws an alarm because the tool is just floating. It's unsecured. The key signal here is that the machine is physically able to complete the motions, but the precision has just drifted.
Okay, and then you have bucket 2, the mechanical jam. This is the scary one, the definitive production stop that sends everyone scrambling.
This is the physical blockage. It means 2 things tried to occupy the same space at the same time.
Right.
So typically the ATC arm is physically stuck mid-swing, or maybe the machine is trying to grab a tool from a pot that hasn't fully retracted.
Or load a tool when there's one already in the spindle.
Yeah, that's a bad one.
And if you're standing nearby, what are you hearing?
It's that definitive grinding or a high-pitched groan. It's the sound of the drive motor stalling under resistance. It's confirmation of a physical conflict.
Which is often because the magazine didn't index right.
Exactly, or a tool pot didn't drop down fully.
Okay, what if the change cycle itself looks unstable, shaky, or it sounds like, I love how our source material put this, a bag of rocks.
That's a perfect description. That's bucket 3, the shakes and noises.
So excessive vibration.
Right, unstable arm movement. If you see the tool bouncing slightly as it's moving, that stability is gone.
Yeah.
It means the drive mechanism is struggling. It could be loose, worn, underpowered.
And that kind of failure leads to other problems pretty fast?
Oh, immediately. That leads you straight to bucket 1, the misalignment, because the arm just can't settle accurately.
And finally, bucket 4, the silent alarm. Machine is running fine, and then nothing.
Dead stop. No noise, no grinding, just a persistent red error code flashing on the screen.
Why? What's happening there?
The machine's logic is fundamentally confused. It might be getting conflicting signals from its proximity switches. It might think the arm is in 2 places at once.
So it thinks the arm's retracted and active at the same time.
Exactly. So the brain just halts the entire cycle to prevent a collision it can't process.
Okay, now that we know what the machine sounds and looks like when it breaks, let's dig into the why.
Right, the root causes.
We're focusing on the mechanical, pneumatic, and electronic culprits. Let's start with the inevitable one, mechanical wear.
The ATC arm assembly is really the unsung hero of the machine. It works harder and faster than almost any other moving part besides the spindle itself.
And every single cycle adds stress.
Every one. Stress on the fingers, the pivot points, the locating pins. This wear is it's unavoidable over time.
So if wear is inevitable, how quickly does that turn into something like the missed handoff?
It's all about rigidity.
Mhm.
Inside the ATC arm fingers, you have these small triangular keys or locating surfaces.
Right.
They're designed to hold the tool holder absolutely square to the arm's axis. As they wear down, the tool holder starts to sag or shift, just ever so slightly.
And that tiny shift is all it takes.
That's all it takes to miss the extremely tight tolerance of the spindle taper. That leads you straight back to bucket 1. A simple visual inspection of those keys can predict a future failure.
Okay, then we have the hidden threat. Pneumatic problems. Air quality is, it's often the last thing people think about in the shop.
But it's the lifeblood of the ATC. Absolutely. Most of them rely on air cylinders to move the tool pots to operate clamps.
And if that pressure drops,
If your shop air pressure dips below that critical threshold, let's say 85 psi for a machine that needs 90 bang, you risk incomplete cycles. The cylinder just doesn't have the oomph to finish its stroke.
and what about sticky solenoid valves? How do they factor in?
Solenoids are precision switches. If you have oil, or worse, water, contaminating your air lines, it forms this sticky, varnish-like residue inside those valves.
So they get gummed up.
They get gummed up. So when the machine commands the pot to drop, the sticky valve slows the airflow. It delays the response. So the arm swings on schedule, but the pot hasn't fully moved.
And that's a crash.
That is a nasty bucket 2 jam. The failure is one of speed, not just alignment. That delay is critical.
Okay, and the final major cause, control and sensors. The machine's nervous system basically operating in a bath of coolant.
Right. The sensors, usually proximity switches, they're the machine's eyes. They're constantly confirming the position of the arm, the pot, everything.
But they're also constantly exposed to coolant and chips.
All day, every day.
And when they get covered.
A thick layer of sludge or chips on a proximity switch can block the signal entirely. This is the #1 cause of the silent alarm, bucket 4.
So the machine is getting bad information.
It thinks a step is complete because the signal is blocked, or it thinks the arm is home and out at the same time. It just locks up. Its internal logic is broken.
There's also the human element here, parameter errors, specifically the z-axis height.
Oh, that parameter, the z-axis tool change position, is arguably the most dangerous one to mess with. If that value is off by even 1/10 of a millimeter,
What happens?
the ATC arm will strike the tool holder at the wrong spot. You can physically bend the tool flange, damage the arm's keys, or even shock load the spindle bearings. It's why machine builders often password protect those parameters.
So we know the symptoms, we know the causes, now the machine's down. We need a concrete, systematic plan. We can't just stare at the error message. Let's walk through the actionable fixes, starting with the finesse required for that missed handoff, the alignment failure.
For misalignment, step 1 is always physical. Use an indicator. Check for worn mechanical parts, specifically those arm fingers and locating pins. If they're showing excessive wear, replace them first. Don't try to adjust around a worn part.
But if the parts are sound, then we move to calibration. How do you reestablish that perfect precision in the control?
You have to access the machine's offset or parameter settings. It's usually under a maintenance screen. You manually jog the spindle down until it is perfectly aligned with the arm's height and orientation.
Very carefully.
With extreme care. Use a dial indicator if you can. Once you confirm that perfect 0 position, you input that new value into the tool change position parameter.
And before you save that parameter, you have to double check the air pressure again.
Absolutely. If your pressure is dipping mid-change, no amount of parameter tuning is going to fix it. You have to fix the air supply problem, the leak or the compressor, before you lock in a new parameter.
Okay, now for the emergency maneuver, unjamming the arm. Bucket 2. The machine is locked up, the motor is stalling. This is where people start to panic.
And this is where you separate the technician from the brute. The critical warning, the one drilled into every service tech, is do not force it.
No pry bars.
No pry bars, no pipes, no external mechanical advantage. You risk shearing a pin, damaging a coupling, or even fracturing the super expensive cam box housing. You can turn a day of downtime into a week of rebuilding.
Okay, so what is the safe manual recovery process?
You have to use the machine's built-in manual recovery. It's usually a combination of buttons you hold to release the motor brake on the ATC drive,
Right.
and then you use a designated tool, a hex wrench, sometimes a hand wheel, to manually turn the mechanism. You rotate it slowly, step by step, until the arm safely backs off the spindle and returns home.
Once it's free, what's the first thing you check to stop it from happening again?
Lubrication. Jams often happen because the mechanism is dry or the grease has just degraded. After you manually cycle it, check all the grease points, make sure it's running smoothly before you even think about trying the automatic cycle.
How do we fix bucket 3? Silencing that noise and vibration.
Noise almost always indicates slack in the mechanical drivetrain. You have to start with loose connections. Check the bolts securing the reduction gear, and critically check the bolts connecting the ATC arm to its pivot shaft.
So it's usually mechanical, not electronic.
Almost always. Tightening a single loose bolt can restore stability immediately.
And if all the connections are tight?
Then you check the transmission components, inspect the belt tension between the motor and the gearbox, check the reducer gear backlash. Too much play will cause that clunking sound when the direction reverses.
So you don't jump to tuning the servo gains?
That's a last resort. The majority of noisy, unstable operation is just a loose component struggling under high torque.
And finally, clearing that silent alarm. The simplest fix, but often the hardest to find.
It's a game of hide and seek with chips. You have to locate the proximity sensor that's throwing the error, and it's very likely just covered in metal chips and dried coolant.
So you wipe it off.
Wipe it off thoroughly and see if the error clears. 9 times out of 10, that's it.
And if cleaning doesn't work, how do you know if the sensor is actually dead?
You do a simple operational test. Proximity sensors have a little LED on their body. You manually place a piece of metal, a wrench, anything in front of the sensor face. The LED should light up.
And if it doesn't?
If the light stays off, or if it stays on constantly when nothing is near it, the sensor's faulty. It needs to be replaced.
That systematic approach is exactly what saves time and prevents catastrophic damage. But let's shift completely now to prevention.
That's the goal. Maintenance is exponentially cheaper than downtime. You can minimize, I'd say, 90% of these failures just by sticking to a religious routine.
So let's define that routine. What does a responsible operator do daily to protect the ATC?
Every single day. First, chip removal. Clear the ATC arm, the tool pots, and specifically wipe down the area around any sensors you can see. Second, check the shop air gauge. Make sure it's consistently above the minimum, which for most high-end ATCs is 90 psi.
And the third critical daily check.
Empty the water separator. That condensed water in the air lines is the natural enemy of solenoid valves. If you let water and oil accumulate, that mixture gets forced into the valve block, gums up the works, and leads to those slow pop movements and sticky valve crashes.
What about the weekly schedule? What needs lubrication?
Weekly, you absolutely must check the oil cup for the ATC lubricator. The cam mechanism needs a steady, sufficient supply of oil to prevent high friction and jamming. If you wait until it's empty, you're already behind.
Beyond the machine itself, we need to talk about how operators use the tool changer, especially with heavy tools.
Operator training is paramount. Never load tools that exceed the magazine's weight limits. But if you are running a heavy tool, one that's near the limit, you have to mitigate the mechanical shock.
How do you do that?
By slowing down the rapid traverse override. Running a heavy tool change at 100% rapid puts tremendous inertial force on the drive motor and keys.
During deceleration.
Exactly. Just dropping the override to 50% or even 25% for that one cycle dramatically reduces wear and the potential for a crash.
And what about that often overlooked issue? A dropped tool.
Tool holder integrity is everything. A loose pull stud is catastrophic. Vibration during machining can cause a poorly torqued stud to loosen even more. A mandatory monthly inspection of pull stud torque is a non-negotiable insurance policy.
Let's circle back to the environment. You had a great analogy about dust creating sandpaper grease.
It's true. Fine metal dust, shop dust, it settles everywhere. When it mixes with the grease inside the cam box or on the tool magazine chain, it creates this gritty, abrasive paste. You're effectively running sandpaper inside a precision gearbox.
So keep the top of the machine clean. And if you see that black, sludgy buildup on the magazine chain,
you have to clean it off and re-grease it immediately. Cleanliness directly correlates to longevity and, crucially, to consistent accuracy in the tool placement.
we've covered a tremendous amount of ground today, from that terrifying grinding sound of a jam to the silent red code of a sensor fault. It is absolutely clear that ATC faults aren't random.
Not at all. They're predictable, and critically, they are fixable by the team on the floor.
Right.
By focusing on the health of your pneumatics, the cleanliness of your sensors, and systematic maintenance of mechanical parts, you retain reliability. You minimize that costly downtime.
So let's leave you with a couple of thoughts to take back to the shop floor. If clean, dry, pressurized air is the critical lifeblood of the ATC,
And it is.
how many production minutes are you truly losing every week across your facility due to small, persistent air leaks? Or poor water separation that everyone just ignores until that catastrophic sticky valve crash happens?
And to expand on that link to the environment, we talked about dust creating an abrasive paste, but consider this. What is the ambient temperature and humidity in your shop? Those factors directly impact the life of sensitive electronics. What seemingly benign, often ignored environmental factor might be secretly contributing to the degradation of your precision proximity sensors, slowly creating those intermittent, hard-to-trace silent alarms. Your operating environment is part of the machine's maintenance schedule, whether you realize it or not.